So hello everyone. I have the great privilege of being the first student talk, so that's exciting. Although you see my full name as per most Latino people, you can just call me Diego. I'm from Ecuador, but I'm doing my first year PhD in Italy, and I'm going to talk about the gamma ray follow-up program at Icecube, which is a real-time alert branch of Icecube. First of all, just in context to talk about multi-messenger astronomy, as we saw earlier today, neutrinos are produced in astrophysical sites along with cosmic rays, gamma rays from cosmic rays alongside gamma rays. The models for which this production happened are still largely unknown to us, largely being decided on. So detecting the neutrinos as well as the other messengers is a probe into high energy phenomena, particularly at the high energies that occur in astrophysical sources like the one I very uglily drew on this corner of the page. Neutrinos have a great advantage over some of the other messengers. Cosmic rays are deflected by magnetic fields, so the further away they are, the less likely we are able to pinpoint their location. Gamma rays don't have this problem. However, gamma rays at very high energies might interact, might be dissipated into the extragalactic background. So there's a limit to what we can observe in gamma rays. Neutrinos, however, travel unimpeded from the sources. However, this happens because neutrinos interact very weakly, and this also raises the problem of detection, which is why we have huge experiments like Icecube to try and detect one every couple of months, hopefully, at best. Which is why complementing the detection of neutrinos with gamma rays, with other messengers from the sources they come from, really helps us get a better picture of the astrophysical landscape. How do we search for neutrinos? Neutrinos observations are dominated by background, mostly the atmosphere, as we saw in the talk here today. However, we expect this background to be mostly uniform. So when we identify excesses over the background coming from specific directions, we can say, okay, there's something interesting happening here. The other way is searching in energy. If events are highly energetic, then they probably pop out from the background. The spectra of the background is different from the spectra we expect from signal. So modeling signal away from the background, also in the plots Maria showed earlier today, should give us an idea of that these events are signal and they can come from astrophysical sources. So what do we do? I'm going to focus here on the detection of tracks in Icecube, which are caused by muon neutrinos, specifically because the shape of these events point very well towards astrophysical sources. Icecube has a great advantage compared to other detectors in the multi-messenger landscape, like the gamma rays. Icecube has a full view of the sky, has close to 100% uptime, so it can serve as a prompt for example, gamma ray telescopes, which are directional and can only operate on certain times of the day, to send alerts when we detect the significant events in time. Here is a shape of more or less what we expect. Also, the background in time for neutrinos is expected to be more or less uniform, so a significant event should pop up in time. This way, Icecube sends alerts of significant events of neutrinos, which allows to follow up observations in gamma rays, in X-rays, in many other scenarios, which can lead to combining measures and get a richer picture of the astrophysical processes. How do we do this in the gamma ray follow-up? We focus on clusters of events, not on significantly single high events, but multiplex of events. We search for flares of neutrino emissions, identifying the excesses in the background and hoping these groups of events help us resolve sources using lower energies than the most significant energies available. This is a very confusing graph, which I'm going to try to explain very quickly. But the idea is to identify flares. Each of these dots in this graph identifies a flare, a group of events that pass a significant, that are deemed enough to be considered a candidate for a significant emission. Once they pass a threshold for significant emission, and statistically, we can send an alert. What happens in each of these little dots? In each of these little dots, we get more or less this process. If an event, all of the events are processed when they arrive to Icecube, we clean out some of the ones that we are sure not going to be interesting, and then we get what they're called GFU events, but that's historically the name of the filter. If an event that has passed all of these passes a threshold in significance over background, then this triggers an analysis. And then we look for maybe this being part of a flare, of a cluster, of a consistent emission over the past 180 days. Now, the time windows that are tested, because you cannot test like every single 1 day, 2 days, 3 days, are defined by other events that previously have passed this threshold. For example, these ones too, these two pairs, and then a likelihood analysis is run with all of the events between these time windows. Once you identify which is the best time window, which is the best cluster that maximizes the possibility of this, you get your flare candidate, you put it in the little significance curve, and if it passes a threshold, an alert is sent. The alert is sent, and now alerts are sent privately to partner gamma telescopes, Cherenkov telescopes in the ground, so that they can follow up on the observation. Right now, we're moving towards public shared alerts. Right now, these alerts are shared privately with partner telescopes. Why? Because in the past years, yes, there is the modeling of the high energy gamma ray processes being connected to neutrino emissions. However, so far we've identified not many sources that satisfy this correlation. We have TXS, which is great, but there's still many other sources. So we're moving towards public shared alerts so that not only these the partner telescope can follow up, but also X-ray telescopes, telescopes that look at galactic sources. Particularly, this leads me to talk about one of the modes in which this program runs, which is the source list. The source list hypothesis tests these flares against specific locations in the sky determined as gamma ray sources, defined by gamma ray telescopes on the ground on the partnership we have with them, which is advantageous because it incentivizes the telescope to look for the sources. Also, the fixed locations mean we're not looking everywhere in the sky to identify excesses. However, we are restricted to limited locations, and as mentioned before, it's still not completely definite the relation just between high energy gamma rays and neutrinos, which is why currently we are expanding the source list. We're renewing the source list to focus beyond gamma rays, on X-ray transients, on microquasars, and on galactic sources. Also, there's the all-sky scan, the all-sky mode, which is not fixed on these specified source lists. Instead, every event that passes the threshold can be treated as a possible source, and then using an algorithm in HillPy, you start scanning the area around it, defining the pixels, and identifying, okay, this is the best location. So we start zooming in a little bit more, making the pixels thinner and thinner until we can define a best fit location. However, because we're looking at a lot of hypotheses in the space, the trial factors are larger, so we need to have a higher confidence before we can send an alert on this. The advantage is that this search is not biased by a specific source, a specific model. In progress, however, is defining a confidence region, a better statistically defined confidence region for these all-sky alerts. Right now, these alerts are sent with a fixed contour of around 0.2 degrees. Don't quote me on that. So the idea is using the statistical results from this analysis to define better, more confidently a region. So we can say, okay, this is our 50% confidence region. This is our 68% confidence region. The way we're doing this is right now we're evaluating that we're taking the space in the p-value in the test statistic that we built and making sure that we are consistently with simulations reporting that our source, if we define a 68% confidence region, falls within that location. This is a little cartoon map I drew, and this is the events, the best fit location, and the hypothetical source simulated. And we would like to be able to draw confidently error levels like this. In conclusion, this GFU program at Icecube searches for flaring neutrino signals from astrophysical sources. Currently, the goal is to trigger follow-up from partner telescopes in high energy gamma rays, but we're moving beyond that to respond to evolving understanding of sources, to follow up also in X-rays and in different parts of the multi-wavelength spectra, and more efficiently triggering the community and more efficiently triggering also analysis that don't have to be done just by prior memorandum of understanding, as well as focusing our sources, our ideas more on what Icecube is interested in. Thank you.
Thank you, Diego. Questions? Any questions? Yeah. Maybe safety.
Hello. So sorry, it's not my field of expertise, so it might be a super naive question, but you have to do actually quite a big process to send an alert, and you might have a time window that is actually, so can you give some numbers or some?
Right now, so the processing of the events is already done in real time. It takes 1 second, then the triggering of the time between. Actually, this doesn't take that long for a single event, for a single test, on the order of seconds. The follow-up from partner telescopes between getting the result for the alert takes some seconds to some minutes, and then sending an alert will take a little bit longer, and then telescopes responding to that alert might take hours. Days.
Okay. Maybe a follow-up, sorry. If you do this trigger in seconds, how many false triggers do you have? Just curiosity.
How many what?
False triggers, like caused by a muon or caused by...
These are built. The thresholds for significance are built so that the false alarm rate is very low. For all sky right now, it's 1. So that the all sky right now, it's an alert 1 per year, and the false alarm rate is very low. For sourceless alerts, this is more confident since we have better test hypothesis, but in general, this is the false alarm rate right now is below 0.1 per year. I think no, for sourceless is maybe 1 per year at the current moment, but it's working on being improved.
Okay.
And we sent like 10 of those units.
Thanks a lot.
More questions? Yeah. Yeah.
Thank you. Very nice talk. So just a quick question on this part. So how do you model the signal that you inject in order to make the calculation of the background and signal simulation?
The background is taken from data.
Yeah. About the signal?
The signal is injected from specific sources, and this signal specifically is we inject in a specific location, and we use a spectral index of around 2.5, which is...
So it's again a soft power law.
Yeah, with a power law.
Mm-hmm. Thanks.
I would say let's thank Diego again.